Good day, I'm Norman Walberger. Today's video is the last video in the first part of this course in the Foundations of Mathematics, where we're having a look at how to set up mathematics correctly. In the second part of the course, which I'm going to start with the next video, we are going to change direction in a major way. Today I'm going to talk about algebraic curves and how we can extend Newton's method to find approximate intersections of algebraic curves. And we're going to look at one particular example. So there's an underlying question here about what exactly is an algebraic curve, and for us the answer is that it's basically a bipoly number. P, say, depending on alpha and beta. Okay, and we'll have a look at two particular algebraic curves. The Fermat curve, which looks like this perhaps. X cubed plus y cubed equals 1 is the traditional Cartesian equation for it. Studied by Fermat. Very important curve. And the second curve is the lemniscate of Bernoulli, an even more important curve investigated by Jacob Bernoulli. Looks like this, and it has equation x squared plus y squared all squared equals 2x squared minus y squared, again in Cartesian coordinates. Now you can see from these two pictures that the red Fermat curve and the blue lemniscate meet at these 2 points. And those are the only 2 points where they meet. And so a natural question is, well, can we find out where those 2 points are? Algebraically, it means solving these two equations simultaneously, which is rather a challenging thing to do. And in fact, you can't do it over the rational numbers. In fact, over the rational numbers, the Fermat curve itself is already very difficult to get a hold of in this form, because Fermat himself proved that the only rational points on this curve are the 2 places where it meets the x and y axis at 1, 0 and 0, 1. There are no other rational numbers, x and y, that satisfy that equation. But nevertheless, we'll see that there is an approximate version of this question. So we can find approximate points here and here that lie approximately on this curve, in the sense that they almost satisfy this equation, and they lie approximately on this curve in the sense that they almost satisfy this equation. And that's what we're going to be after. That's what Newton's method allows us to find. It allows us to find an approximate solution to an equation, which in practice is all that we can expect and hope for, and all that we often need. So let's start by having a look at the Fermat curve. X cubed plus y cubed equals 1. The associated bipoly number is this one here, minus 1 plus alpha cubed plus beta cubed, where alpha is playing the role of x and beta is playing the role of y. So this fits into our polynumber framework, which is a very explicit and computationally simple way of dealing with polynomials. Now, when we talked about bipoly numbers like this some time ago, I told you that there were a number of different interpretations of such a polynumber. There are different ways of visualizing or imagining what this expression represents. And I explained that we have to sometimes have a flexible attitude as to what interpretation we're going to be using. So one interpretation of such a polynumber is interpretation A, where we interpret it as a curve, P of x, y equals 0. So in other words, we're setting the equation or expression equal to 0 and looking to see where we can have some solutions in the plane. That's where we get the familiar equation x cubed plus y cubed equals 1 from, and that's where this picture comes from. This is a curve in the plane, at least we can see it. And what we're really graphing here are not points that exactly satisfy this equation, but points which approximately satisfy this equation. So this is a picture of rational numbers, all kinds of rational numbers, x and y, such that x cubed plus y cubed is pretty close to 1. And pretty close is variable depending on your computer program, depending on the resolution that you want to obtain. It's a curve. It's a two-dimensional picture. Then there's also interpretation B, which is different. We take the expression now and we create from it a surface by essentially looking at this equation, by introducing a third variable z and thinking about the surface z equals p of xy. So for any two values x and y, we can compute p of xy, that's a number, and then that's going to give us the height above the point xy that the surface lies on. So here's our three-dimensional picture, or at least a two-dimensional representation of it. The x direction coming out at us, the y direction in the board, the z direction in the board. So the xy plane that was visualized over here in this way is now visualized lying horizontally with the x-axis coming out at us here and the y-axis there. So what was the curve over here is now this red curve that you see lying on the horizontal xy plane. But that's only a part of the object over here. The object is actually the surface itself, and that's a surface in space. As it turns out, if you look at it in this form, z equals x cubed plus y cubed minus 1, if you go in the positive x and the positive y direction, the surface is coming up. In other words, the z coordinate is increasing. While if x and y are negative, so we're going in that direction, then these terms will become negative and the z coordinate is going down. In the sort of 45-degree directions here, roughly the x and the y terms will balance themselves out and the z value will be pretty close to 0. So it's a little bit of a hard thing to imagine, but you can roughly visualize this surface in the following way. That if you're sitting at the origin and you have your back to the positive quadrant, so you're back to the x and y directions where they're going positive, then it's almost like you could sit there with your back against the surface and your feet hanging over the edge where the surface goes down, and you could have your arms stretched out in these directions here, and the surface would be more or less horizontal there. And the curve that's visualized here is just the places where that surface cuts the xy plane, or where it approximately cuts the xy plane. So admittedly, it's more difficult to visualize. But there's an important way in which this picture is simpler than this one. And that is that this is actually a function, in the sense that if you given any value of x and any value of y, you just compute the value of z to find a point on the surface. So we can find lots of points on the surface very easily, because this is just an equation that can easily be used to generate triples x, y, and z. On the other hand, this picture, while two-dimensional, is harder and more conceptually difficult because we can't actually find points which satisfy this relation so easily, exactly. So we'll see that for the problem of the meat of the Fermat curve and the lemniscate, this picture here is the one that helps us apply Newton's method successfully. So let's use the ideas of the algebraic calculus that I've set up so far to deal with polynumbers to analyze this Fermat curve, in particular to get some tangent line or tangent plane to it. So we're after the tangent plane to the Fermat curve, and you might want to review Math Foundation 78, where we dealt with a simpler situation of the unit circle. So we're going to be doing the same thing here that we did for the unit circle, so you might want to review that simpler situation first. There's our polynumber. minus 1 plus alpha cubed plus beta cubed. First order of business to find the Taylor polynumber, just obtained by replacing alpha with alpha plus r and beta with beta plus s. So we get this expression. Then we expand out using the binomial theorem. You can check that we get all those terms. And they are then written in increasing powers of alpha and beta. Constant term, alpha, beta, alpha squared, beta squared, and alpha cubed, beta cubed terms. And now what we do is we essentially go back to the original polynumber by, in this expression here, replacing alpha with alpha minus r and beta with beta minus s. That gives us p of alpha beta equals then exactly the same expression with the alpha replaced with alpha minus r and the beta replaced with beta minus s. This expression is the Taylor expansion of p at the point rs. It's a rewriting of the polynumber in powers of alpha minus r and beta minus s instead of in powers of alpha and beta. Now what we can do with this expression is we can read off the various tangents to this bipoly And the one that we're interested in is the first tangent. What we get when we just go up to the linear terms and disregard the higher terms. So we're just going up to there and copying that again. There it is right there. We can simplify that by expanding these things out, combining here, and we get minus 1 minus 2r cubed minus 2s cubed, constant term, plus 3r squared alpha plus 3s squared beta. That's the first tangent to p at the point rs. And we'll interpret that as the tangent plane to p at the point rs. An important point to emphasize to you is that we have not done anything other than high school algebra. Very simple manipulations to get our tangent, our first tangent. No limits have been involved and no real numbers have been involved. And in fact, we've avoided even the idea of a derivative. It's been very simple. So there are two interpretations of this bipoly number. One is as a tangent line of some kind in the xy plane. Another is as a tangent plane in the xyz space. Let's think about the interpretation B first, because that's the one that's going to be more important for us, at least to orient ourselves. We've talked about the surface determined by the original Fermat curve. And now we have a point RS in the xy plane. So it is in the horizontal plane. And above this point, or below it perhaps, depending on where you are, in this case above this point, there will be a point on the surface. And that surface is inclined in a certain way above the point RS, and there's a tangent plane to the surface at that point. And it's that tangent plane to the surface at the point above RS that we are calculating here. This, if we set it equal to z, is a linear equation in x, y, and z that represents a plane in three-dimensional space, which is exactly the tangent to the surface. Another interpretation of this bipolar number is to set it equal to 0. Then we get something that lies only in the xy plane. And that's exactly just the meat of this tangent plane in three-dimensional space with the xy plane. So in this picture I've represented the tangent plane by this green parallelogram there. That represents the tangent plane. And where it cuts the xy plane, I've represented that by this line in red. So if you have a two-dimensional point of view, you say that this thing represents this red line in the xy plane. If you have a three-dimensional point of view, you could say that this represents the tangent plane to the surface in the three-dimensional space. Now let's turn our attention to the lemniscate of Bernoulli. which was one of the most important curves introduced into the 17th century and played a very important role in the development of mathematics, especially in the direction of elliptic curves and elliptic integrals. A little bit of that story is described in my Math History 14 lecture, which I actually haven't quite posted yet. Alright, so here's the lemniscate of Bernoulli. It's like a figure 8, and in fact it's the symbol for infinity that is commonly used. That was introduced by Wallis. And this equation arises in a very nice geometrical way as the equation satisfied by a point x such that the product of its quadrances to the point f1 and the point f2 is equal to 1. So f1 is the point on the x-axis with coordinate 1, and f2 is the point with coordinate -1. We're looking at some variable point x, and we're looking at this quadrant times this quadrant equaling 1. That condition maps out this lemniscate. If you can't remember what quadrants is, well, shame on you. Then you need to go back to the geometry section of this series and remind yourself about that important notion. So, also an oval of Cassini this is, because this kind of condition was generalized to have a more general value here, and you get more general ovals. This is a special case. The lemniscate is also associated to a torus or a donut. If you have a circle which revolves around like this, so that that diameter is the same as that diameter, you get a torus. And then if you slice that torus with a plane, exactly a tangent plane to a point in the interior of this inner circle, then the cross section that you get is a lemniscate. Alright, so we can take this equation in x and y, bring all the terms to one side if we like, replace x with alpha, y with beta, and we get an associated bi-Pauli number. Minus 2 alpha squared plus 2 beta squared plus alpha to the fourth plus 2 alpha squared beta squared plus beta to the fourth. That's a bi-Pauli number that captures all this geometrical stuff, and we can work algebraically with it. So our aim now is to find the first tangent to this thing. Okay, so the first thing that we do, we calculate the Taylor Pauli number by replacing alpha with alpha plus r and beta with beta plus s. And there's what we get. And now we're going to write that out. We're going to expand that out in powers of alpha and beta. And because we're interested in the tangent line, or the tangent plane, essentially the first tangent to this Pauli number, we're not going to do all of the work. We're only going to go up to the linear terms in alpha and beta. The rest, actually, we don't care about for this particular application. So we can save ourselves a lot of work. So we're just expanding this out and looking for the terms that don't involve any alphas and betas. That's those ones there. And then the ones involving alpha, we group together. The ones involving beta, we group together. So for example, this term 4s cubed beta, where does that come from? It comes from this expression here. When we expand that out with the binomial theorem, we're going to get 4s cubed times beta. That's where we get that term from. And similarly for these other terms. Then how do we get the tangent plane, or the first tangent to P at Rs? We take the linear part of this Taylor bi-Pauli number, disregard all the quadratic and higher terms, and replace the alpha with alpha minus r and the beta with beta minus s. So exactly what I'm doing here, I'm copying that. That's copied there. This term right here with an alpha minus r now, and this term with a beta minus s. And then now we write this out, expand it out, put it in the standard form, and I'm going to rewrite it with, instead of alphas and betas, x's and y's instead of alpha and beta. So you check my algebra there, that I've expanded this out and rearranged it in a pleasant way. I've just simplified it a little bit to make it a little bit more pleasant. So what is this? It's the first tangent to the bipolar number. It represents our tangent plane to the surface of the lemniscate. So let's put these two pictures together. And we're going to do it on a two-dimensional picture, because drawing that three-dimensional picture and imagining those surfaces and drawing them accurately is, well, something that requires too much work. The two-dimensional picture we can deal with very easily, but we're going to think three-dimensionally. All right, so there's our Fermat curve. There's our lemniscate. And here are the equations of the first tangents to the Fermat curve and to the lemniscate for a point RS. That was the one for the Fermat curve with R's and S's involved, otherwise linear in X and Y. And here is the expression for the lemniscate tangent, also involving R and S and linear in X and Y. Now, to focus our minds, let's choose a particular point RS. I'm going to choose this point right here, 2, 1. 2 in the X direction, 1 in the Y direction. There it is right there. We're going to look at the tangent planes to these two surfaces at this point here. Well, what we do is we replace R with 2 and S with 1 in both of these equations. Now, in terms of the tangent planes, remember the surface for the Fermat curve is something that lies over this two-dimensional picture, and it's a surface that goes up. If, say, this is the Z direction now, and I'm going to use the plane of the board as the XY plane, it's a surface that's going up as we increase X and Y. And lying over the point RS, there will be a tangent plane. Okay? And that tangent plane has equation Z equals this. These are the values that we get when we plug R equals 2 and S equals 1 into this equation here. Now that tangent plane in this three-dimensional situation cuts the XY plane in this red line. That red line is what we get when we set this equal to 0. So we can say that this line is the tangent to the Fermat curve at this point A1. That's probably a novel way of thinking for you, because you're used to curves only having tangents at points which lie on the curves. So if A1 happened to be actually on the curve, say there, we would be talking about that tangent. This is a more flexible notion of tangent, which is quite useful and almost never seen in calculus texts. I recommend it to you. Okay, so we have a point there. There's the tangent line to the Fermat curve at that point. It's where the tangent plane of the corresponding surface comes down and crosses the XY plane. So what's the surface of the lemniscate look like? Well, it's a little bit complicated to explain without a picture. The picture is sort of two valleys coming down. So there's a valley here and a valley there, and otherwise the mountain kind of comes out. So as we move out here, these things get bigger, and we get sort of oval-shaped level curves. So at this point here, the surface is going to be out here like this, and there's going to be another tangent plane to the surface above this point, and that tangent plane is going to meet the XY plane in this blue line. And the equation of that is obtained by taking this and substituting R equals 2 and S equals 1, and then setting it equal to 0, and this is that line. Okay, so we've got these two tangent lines corresponding to this point, and if the point actually here was pretty close to being where these two curves meet, then these two tangent lines would be pretty close to being tangents at the two curves, and where those two tangents meet would be a pretty good approximation to actually where the curves meet. So our strategy is to use where the two tangents meet as our next approximate point of intersection. This is a kind of Newton's method, an iteration where we use the tangent to determine a new point, but now we have two tangents, and so we're going to use the point where they meet as our new point. So where do these two lines meet? Well, you need to solve these two equations. These are two linear equations in x and y. And if you solve them, you will see that the point of intersection right here is 83 over 64, 55 over 48. And then we can repeat the process using this point now instead of the first one. We can figure out what is the tangent to the Fermat curve and the lemniscate at this point, namely when r is this and when s is this. Plug those back in there. Well, it turns out that the Fermat curve has tangent this one here, and the lemniscate has tangent this one here, and those two lines will meet at this new point A3. So we can iterate. And if we keep going, we're going to get closer and closer to that meet of the two algebraic curves. This is Newton's method applied to two algebraic curves, and they are not functions, they're actually algebraic curves. So this is a more general and somewhat more powerful method than the one that's usually used and that's usually found in calculus texts. And we're doing everything over the rational numbers. To give you a sense of the numbers involved, at the next iteration, the value of A3 looks like this. It's already pretty big, and A4 is considerably bigger. So to go further, if your computer can deal happily with these big rational numbers, fine. Otherwise, practically, if you were doing it yourself, you would want to approximate these numbers with decimal numbers and just work with decimal numbers. So for example, with decimal numbers, the sixth one turns out to be something like this. This turns out to be accurate to 3 decimal places. The seventh one looks like this. That's accurate to 6 decimal places. So we're zooming in on this approximate point. Of course, there is no actual point where these two curves meet. We're only talking about approximations. But that's what we want to do in mathematics often. We just want to find an approximate place where these two curves meet. That's all that we can do, in fact. Okay, so this is a rather advanced application. I'll give you an exercise if you like and want to practice. You can see if you can find that other intersection point, the one down here, using similar kind of technology. So the basic equations for the tangent planes that I wrote down, or the tangent lines in the two-dimensional picture, that's really all that you need to generate this iteration of getting from one approximation to the next one. Okay, so that's reasonably sophisticated. If you've been able to follow that, fine. If you haven't, don't worry too much. Next time we are going to shift gears in a major way. You can see that I'm getting closer to wanting to do calculus in a systematic way. In fact, I have been doing a kind of a calculus for many of the last few videos. But we are getting to the point now where we're bumping into the calculus which is already there. And I need to address perhaps a painful issue that I've been skirting up till now. We have to face the fact that modern analysis, or modern calculus, doesn't really work logically. And it's my responsibility, I suppose, to set this argument out clearly and to lay out the difficulties that are there. My fellow colleagues seem to be reluctant to take up this challenge. But it's very important that we admit to the weaknesses that are in our subject. Next time we're going to start the new part of this course, where we become a little bit more aggressive and we aim our attention towards the weaknesses in modern pure mathematics. So rather interesting, going to be challenging, certainly going to be controversial. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.